Hi guys, welcome back. This is a continuation of your IMF's notes. So we're picking up where we left off. We're starting with dipole-dipole forces. So the last one we talked about was London dispersion forces. Those were the weakest ones. Now we're talking about sort of the mid-range one here, and these are dipole-dipole forces. So dipole-dipole forces are a force that exists in all polar molecules. Remember, in polar molecules, we see a dipole moment that exists. So that sort of makes sense. So polar molecules have permanent dipoles, whereas that last one we looked at, those London dispersion forces, had these temporary dipole moments that only lasted a few seconds. These polar molecules have these permanent dipoles, so these forces are slightly stronger than those London dispersion forces. And essentially what that's just going to look like is the positive end of one permanent dipole is going to be lined up or attracted to the negative end of another, and it's going to create a dipole-dipole force. Let's take a look. So let's look at the example of CH2O, that's formaldehyde, and this is a polar molecule, meaning it has dipole moments. So I went ahead and drew this out for you here. Here is the Lewis structure for it, if we look at the bond between C and H, it has a 0.4. Between C and H, it has an electronegativity difference of 0.4, and the difference between C and O, it has an electronegativity difference of 1.0. So because this is so sort of on the edge of really having much electronegativity, we're actually only going to look at this this difference in electronegativity, which makes this molecule slightly negative on this top side and slightly positive on the bottom. So it does have a dipole moment that is existing here, and it also makes this molecule polar. So if I were to line these up and show you, because remember, dipole-dipole, this is looking at an intramolecular force, right? This would be looking at how we're bonding this carbon, or how this carbon and this oxygen are attached together. But what we want to look at is two formaldehyde molecules attached to each other, because we're talking about intermolecular forces. So here I'm going to have my slightly negative end. This is going to be, the red is represented in my oxygen, these are my two hydrogens, and the black is my carbon here. So I've got my slightly negative end and my slightly positive end for my oxygen and my carbon, and the dipole-dipole force is going to exist between the slightly positive end and the slightly negative end. So this is going to create a dipole-dipole. The negative end is attracted to the positive end. Okay? So that's what a dipole-dipole is. Now a little reminder here, polar molecules also have London dispersion forces, because remember I said in the previous PowerPoint, London dispersion forces are present in all atoms and molecules. Well, these are atoms and molecules, so not only does this have a dipole-dipole force, it also has a London dispersion force present as well. So dipole-dipole forces therefore give polar molecules higher melting and boiling points. So the stronger the intermolecular force, remember we said that, the higher the melting and boiling points are. So these therefore should be higher than non-polar molecules of a similar molar mass. So let me show you what that means. So look at the molar mass of each of these two molecules. So we've got formaldehyde, which has an approximate molar mass of 30, and ethane, which has an approximate molar mass of 30.1. Now remember, in the previous PowerPoint, we said that as you increase in molar mass, you should increase in your boiling points and your melting points. So the ones that have the higher molar mass should have the higher boiling points. Well, these have the same molar mass, so therefore they should have the same melting points. But one is polar, formaldehyde, and ethane is non-polar. So because this is polar, because it has dipole-dipole forces in it, that actually increases the boiling point and makes it have a higher boiling point than the ethane does. So these dipole-dipole forces are stronger, and it makes that boiling point much higher. Okay? Okay, let's take a look at an example of this. So determine whether each molecule has dipole-dipole forces. So we're looking at CO2, CH2Cl2, and CH4. So let's look at CO2. I went ahead and drew out the Lewis structure for you, and I also drew out the dipole moments. So this one, these dipole moments don't have a net dipole moment. They actually cancel each other out. They do have dipole moments, but the dipole moments cancel each other out. So this is nonpolar, meaning there are actually no dipole-dipole forces present. Now, if we look at CH2Cl2, we have one that's polar, one that's nonpolar, but because these don't all cancel each other out, we do end up with a net polarity or a net electronegativity that we can calculate. So we do have a polar bond here, which means we do have dipole-dipole forces present. So when these line up, this slightly negative end will attach to a slightly positive end. Okay, and then this molecule, CH4, is nonpolar, so there will be no dipole-dipole forces present here. Okay, and this is where you're going to pause and do the U-try, and you'll determine whether each molecule has a dipole-dipole force or not. And you'll do that for Cl4, I'm sorry, this is not Cl4, this is Ci4, CH3Cl, and HCl. So go ahead and pause here, and I'll go over the answers on the next slide. Okay, here we go. So determine whether each molecule has a dipole-dipole forces or not. So here's Ci4. Ci4 is nonpolar, so there are no dipole moments. CH3Cl is polar. It has net electronegativity that can be added up because not everything cancels out. So it does have a dipole-dipole moment. And HCl is polar, and it also has a dipole-dipole moment. Okay, or a dipole-dipole force. All right, guys, that's it for this one. Come back again and we'll talk about hydrogen bonding. All right, thank you.